Welcome everybody, and this is actually going to be a little bit of a foray into a program called Geometer Sketchpad, which I don't really have a great um, super developed sense on how to manage, except for the fact that it's fun, it's pretty cheap, it looks pretty much like Geometer, like GeoGebra, and what I'm going to do here is I'm just going to show you one more time, or the first time, or the fifth time, how the method of sections work, and you're going to need to be a little bit open to this kind of sketch. In that I have, in fact, a truss kind of that's defined in some way by D all the way across a 40-foot cross with about 6.66. It's a 412 truss. And I've essentially, in some way, shape, or form, at least showed you right here that you're going to be cutting essentially through this structure, through AG all the way right in through here. And what we've done is we've kind of done some of the moments about A, which of course would take that one out of it and this one out of the equation. And we are showing the reaction within this member down here, which is shown by GF, to a force that's applied right here at ED. Now, of course, that force at ED would be due to, and I'll just kind of sketch that up here, some force that would have been applied down here, right? So that external force would have been applied there, and that external force would then, I'll do edit undo, would have been reacted at ED and over here on the right side. So I'll erase that. And so what you're doing typically, however, edit, cut, is you're now doing essentially a section right through here and doing a sum of the moments. And so here's how the math works. You have the force here, which is the length, right? Right here. E, you see how it's raising? It's 6, or now it's around 4. And I'm making it straight up for now. You've got a force at D up in the E direction. And so that's the force there. If you write your sum of the moments here about A, which would be the point of concurrency of these two lines of direction, or lines of force, what the torque of that is in fact force times orthogonal distance. And so as I'm going to show you here, as I go ahead and change it, you see that that orthogonal distance is changing. Now, because of this, you can kind of take it to the extreme, right? But you can see that it is both the direction of the force and the magnitude of the force that makes the moment. Now, reacting inside of that, there's one other member that can react, and that's this tension, assumed tension here in the member coming out of G, basically. And so you have a ratio of the AB distance to this AC distance down here, which was not necessarily still labeled. I'll try to show you, see if it labels it. I can take right click there, show label, and you see AC there. So that, in fact, is the ratio. You know that this reactive force, GF, is going to be related to the force at D, ED, and then multiply by a ratio of the distance from the fulcrum for the reactive force at the support and the reactive force in that bottom chord of the structure, or of the member, of the truss here. And so by going through that mathematics, you can start to realize, right, moving these things around. You can try it in Geometry, you can try it in AutoCAD and Inventor, but this Geometer Sketchpad, probably a 30-day trial, great, $30 or something like that. It's not so much. Great stuff, especially if you're looking at then tying some of this information into CAD and the like. So I do that. Now, I'm going to try something now within, now that we've got the basic structure laid out, what other things could be done? Well, let's say you went ahead now that you have actually parameterized and constrained the structure. Now, instead of what we were doing there, I can move this structure up this way. So I'm going to, once again, you're going to realize I now have taken that from a 412 truss to a 612 truss. And which means, notice how this works, I think. As I get to there, it will, now you'll start to get a better idea of an equal size, right? The idea that if our truss is pretty long out there, we're looking at the force of reaction in this member and being the same as the reaction force. So if you notice here, because it's a 1-to-1 ratio, you get this reaction force about equal to the internal reaction force equal to about the other one. Let's take it down the other way now and make it a thinner truss approaching what might be a beam. Let's say something really thin. Now this time you won't even be able to read it, but the fact is, because of this reaction here, it's a lot farther out. Now I'm not going to even try to zoom out, but I'll let you know that you can read the value here. So you have in this case, the reaction force, if it would be at E, at D, is in the order of 11. And in fact, the internal reaction of this member down here is somewhere in the 68, it being based on a ratio of 18. So I'll go ahead and pull this back up, take it back to where it was, which is basically at our 412, and you get that sense for both for trusses and then eventually for beams, why in effect the depth of the truss or the depth of the beam kind of reduces the maximum stresses because there is a larger moment arm with which to react to forces, a bigger fulcrum. So the program, Geometer Sketchpad. The process, force times orthogonal distance. Once again, I'll show you. Let's back here. I'm going to go here and realize as I pull this thing in different directions, right? You can see here how that can all the way shorten up, because if in fact the member is such, it might be that there is no internal reaction per se where it was there. So if you notice here, that goes up and down. So pretty straightforward to lay out. And there's lots of videos out for this. You probably want to learn to do it in GeoGebra if you can, but definitely a good $20 to $30 hit at some point in your future for Geometer Sketchpad. It'll help you to do parametric constraints in AutoCAD or Inventor. And it does lots of other stuff, which I'll try to demonstrate really quickly before I finish out this video here by just kind of trying something here. I'm going to go ahead now, and I'm going to, there's a picture, I got a picture, I'm going to bring that picture up. I'm going to bring this picture in, there it is, there's a picture of my local school. I'm going to go ahead and just drop it right inside of here. Okay, there it is. Now I'm going to kind of zoom out. That's great. Kind of a big picture. You can get the idea. I'm going to do edit, cut that picture, which is great because now when I do this and grab 1, 2, 3, right click now. Sorry, grabbing 1, 2, 3, and doing edit, paste picture, you'll see it come in a little differently now. So now when I go ahead and do this stuff, you can start to see how it's morphed and transformed. So we've talked a lot about transformations and in terms of being rotations and flips. There's also one called shear, and one thing that will, not necessarily completely relate is within these structures of trusses, because all the forces are assumed to be and generally are compression or tensions, you don't get these shear failures that you would typically in other members. You'll get a compressive or a tensile failure. There is shear developed, but generally if you've got a complete compression in a member, complete tension, there is no shear. Shear comes from bending. And so just kind of a fun relationship there and a fun piece of software that will help you to play and visualize. Within AutoCAD, this is all done by parametrics, so I'll encourage some of you to do that. You want to get to the point, however, of being able to realize that all that's changing here is not the geometry so much, or the topology, if you would, but actually the coordinates of the point. So there's just a bunch of R cross F going on here, with in fact the R now being determined by 0.2 minus 0.1, and then you're just changing the value, in this case of 1 point, so the rest of the equations kind of follow along. Thanks for listening, and that will kind of complete the conceptual version of moments before we moments and the method of moments or method of sections before we really throw all this together in the mixer of how parametrics work within these modeling engines like Revit, Inventor, SketchUp, your calculator, and a sheet of paper. R cross F. Thanks for listening.